Hello, my name is Rodrigo Borges Sino. My professor is Ginter Kellerman, and my scientific initiation study is about the development of a sample holder for studies by SAXS of nanoparticles embedded in liquids. What is SAXS? Small angle X-ray scattering, or SAXS, technique allows the characterization of the structure of nanocomposite materials. Among the applications possibilities of this technique is the study of nanoparticles embedded in liquids, such as proteins and micelles in solution. In many cases, it is possible to use it to determine the size distribution of nanoparticles with the same shape or the shape of identical ones. Here is a schematic layout of SAXS. The scattered beam is detected in a two-dimensional position-sensitive detector, or PSD. Objective. The objective of this study was to design and build a sample holder for liquid samples of studies by SAXS. The challenge in this case is to keep the sample characteristics unchanged during the period in which measurements are taken. For this purpose, it is necessary to keep the sample sealed to prevent its evaporation and consequently changes in the concentration of the nanoparticles or the formation of bubbles. The sample holder must have an entrance window through which the X-ray beam coming from the source can focus on the sample, as well as an exit window through which the radiation scattered by the nanoparticles can reach the detector. The windows should absorb and scatter X-ray as little as possible and have a uniform diffraction pattern, so removing them from the data is easy. The area between the curves is how much of the X-ray were absorbed by the mineral mica window. For the sample holder, a design was used where the sample is injected by a commercial syringe, which makes it possible to inject the liquid in a controlled manner. Perpendicular to the window will have two openings. One of these openings will be where the syringe is placed. The syringe needle will be glued into a hole in the body of the brass sample holder. The tip of the needle connects directly to the space where the sample is injected, which shall minimize the sample volume required for the experiment. An opening in the opposite side allows air to escape during sample injection. In addition, it can be sealed for air tightness. To check which material would be best for the sample holder window, three materials were tested: Kapton, mylar, and mineral mica. In total, 10 measurements were carried out with the following experimental arrangements. After the measurements, we obtained 10 image files with the diffraction patterns obtained by the PSD, such as the following. Here's a base measurement without the sample and without the paraffin, a measurement with Kapton and paraffin, and a measurement with mylar and paraffin. After that, an angular average is calculated, creating a .xy file. We then change the coordinates of the scattering angle to theta to the scattering vector, as it relates the scattering vector to the wavelength, using the following formula for the magnitude of the wave vector. Results. The sample holder we have designed and described here successfully fulfills the objectives set forth. Here's a technical drawing of said sample holder. We then can analyze the graphs. We can then calculate the attenuation by applying the formula for each materials. The attenuation is the amount of X-ray each window absorbs. This allows us to isolate the contribution solely from the window in the reading. The Kapton window absorbed 6.2% of the diffracted X-rays. The mylar window absorbed 1.22% of the diffracted X-rays. The mica window absorbed 36.65% of the diffracted X-rays. We can then isolate the contribution of the windows to the diffraction patterns, resulting in the following graph. Conclusion. The design presented has fulfilled the previously set objectives. Considering the irregular patterns of Kapton and mylar material, we opted for mineral mica windows. Despite mica windows having a higher X-ray absorption rate, they display a significantly more uniform pattern compared to other alternatives. Moreover, reducing the thickness of the mica window enables us to exponentially decrease its attenuation, thereby mitigating this issue. Subsequently, it will undergo a testing phase in a SAXS instrument at LARCSI of the Physics Department of UFPR. Here are the references for my study. Thank you very much for listening. Have a great day.